Okay, good morning, folks. Just a quick reminder before we get into the lecture material today that there is a student opinion survey that's live. That's not the right QR code. Now I think about it, that's from last year. But the QR code is in the slides from last day. I just checked, and I think one more person filled out the survey after a reminder last Friday. So please go and fill out the survey. That'll help me make the course better for next year. And if you want to go find the right QR code, it's either in the slides that I posted from last time, or you can go to the email that I sent around last week that had the link to go to complete the survey. For the last few days, we've been talking about flexural members, and we're pretty much done talking about how strong flexural members need to be. Okay, so we looked at braced beams, and depending on the section class, we did ZFY or SFY with a resistance factor to get the bending moment resistance. For unbraced beams, we also had to consider lateral torsional buckling, and that depended on how long the unbraced segment length was L and what the shape of the moment diagram looked like. Joists are fully laterally braced, so it just depends on whether it's class 1, 2, 3, or 4. Girders are unbraced between joists, and so you go through the exercise of calculating L, calculating omega 2, getting MU, and then figuring out what your moment resistance should be based on that moment. Last day we looked at the shear resistance of our webs, of our I shapes. We're really focusing on I shapes as beams because 95% of the time we're using a wide flange section. And they could either fully plastify, experience inelastic buckling under shear, or elastic buckling under shear, and it all depended on how thin the web was relative to its height. Today we're going to start talking about how flexible beams are and how we need to limit deflections to prevent cracking of certain components of steel structures. And for the most part, I'm not really going to show you anything new today. I hope I'm not showing you anything new today. But I'm going to place the stuff that you already know in the context of steel design and the stuff that we've been talking about so far in this course. Okay, so today we're talking about deflection of steel beams. For the most part, deflection becomes an issue the longer the beam gets. And for the most part, because of the way we frame everything, they tend to be most critical for joists compared to girders in our structure. There's a little bit of stuff in the course textbook on under section 5.9 limitations of deflection. I actually haven't read that section, but I'm sure it's useful to go through that component. I don't imagine that you're going to need to go through that. Everything that we're going to talk about today should give you everything you need to know about deflection of steel beams in the simple framing that you're working with for the design projects in the course. Basically, after today, you should identify the loads that contribute to deflections with the potential to damage floor finishes. Pretty much everything we're going to be talking about today is in the context of protecting the stuff that is on the floor from damage under excessive deflection. And so this just we've talked about dead, live, and snow loads on structures. Not all of the dead, live, and snow load that contribute to the shear moment that we designed for will contribute to the deflections that we're trying to limit. Okay, so that's going to be a key for today. Should be able to calculate the maximum deflection for simple beams using the MBCC load combinations for serviceability limit states. So I showed you that in lecture 15, I think, for serviceability of tension members. We'll see how that applies to deflection calculations for steel beams. And you should be able to compare the maximum deflection that you get using those calculations to the maximum limits on deflection, and those are recommendations that are found in Annex D of the steel standard. Does anyone have any questions about why these three things are important to be able to do before we get into the technical material for the morning? Okay. So very quickly, just to see what you remember doing. Apparently I can't spell. I'm missing an L in should. But you've calculated deflections a bunch of different ways. I'm wondering if you were to sit down today and I said, hey, I need you to calculate the deflection of this steel beam, would you integrate the curvature twice and apply boundary conditions? Would you apply a virtual load of 1 to the beam at the point of maximum deflection? Would you apply a point load P to the point of maximum deflection, perhaps apply Castigliano's theorem? Or would you draw tangent lines and apply the moment area theorems? I don't even know if you learn moment area theorems in CE 2033 anymore. But you certainly do the first one. In our program in mechanics of materials, you would learn to integrate the curvature twice. What would you sit down and do automatically if you're going to try and calculate deflections? Well, point A got completely wiped out there. I'm not sure where those 7 responses went. And they're back, okay. Interesting. So in any case, I mean, this is stuff that you learned in CE 2023, Mechanics and Materials. You probably review it also in 2033. And then all the other stuff is in 2033, right? So point load of 1 at the middle of the beam, that's virtual work. Point load of P to the center of the beam, apply Castigliano's theorem. I don't even know if you learn moment area theorems anymore. But basically, everyone's comfortable with the stuff that you don't talk about in 2033, which is always fun. In this course, we're not going to do any of these things, right? So on assignment 0, I talked briefly about doing the integration by integrating the curvature diagram twice, then apply the boundary conditions to get deflection equations. For the most part in steel design, you don't care about the shape of the deflections. You just care about what the maximum deflection is going to be. 1% of the time you might care about the shape, but for the most part, we're just looking at the maximum deflection that we want to calculate. And honestly, virtual work's probably the easiest one to do there. So part B is probably the easiest thing, but there's some stuff that's even easier. And we'll talk about those basically for the rest of the day. Okay, so the 7 of you who said I would do integration of the M over EI diagram twice and apply boundary conditions to get my maximum deflection. For a simple beam with uniformly distributed load, you'd be doing something like this, right? You'd get the load on the joist from the tributary width and the uniform pressure that's applied to the floor area. You'd make a section cut somewhere at distance X, and you would figure out what the internal bending moment is, and you'd say, okay, well, under this situation, we've got the uniformly distributed load, we've got, pardon me, the reaction WL over 2 at the left-hand side, and so your moment diagram would be WX squared over 2 minus WLX over 2. And then you'd say, okay, I'm going to integrate that a few different times, right? So I'll integrate it once. The first time I integrate, I'm going to get an integration constant C. The second time you integrate it, you're going to get an integration constant D. And then you apply the boundary conditions, right? You know that this equation, delta, at x is equal to 0, should give you 0. There's no deflection at pins. And so that would mean this is 0, and this is 0. And so D would also have to be equal to 0 in that case. And applying the boundary condition at the right-hand side, you do the same thing. You get an integration constant. Not trying to review deflection calculations here. What I'm trying to demonstrate here is that after you finish that process, what you're left with is an equation for the deflection along the length of the beam that you can use to figure out the deflection anywhere, right? That was the whole goal of doing the double integration of the curvature diagram. So you could say, well, where do I want my deflection? It doesn't matter. You just plug in a value of x into that equation, and you would calculate the deflection at that location. So that's great. I don't care, though. I don't care what the shape of the deflection is. I just care about the maximum value of that diagram. Now, you could do some calculus to find maximum whatever. I'm not going to do calculus to find maximum values. Where's the maximum deflection on a beam that's uniformly loaded and has simple supports at the left and right-hand side? Where's the max deflection going to be? At L over 2, right? It's going to be, it's a symmetrically loaded beam, so the deflected shape is going to look something like this, and my maximum value of deflection is going to be at L over 2. So if I want my maximum deflection, I can just say x is equal to L over 2. I can plug that into this equation, and what I'm going to get is I'm going to get 5 W L to the 4th over 384 EI. Right, so that's an equation I talked about in assignment 0. Does everyone remember that equation? You must talk about it in either, right, structural analysis or mechanics and materials. This is the equation that I'm going to use to get the maximum deflection, which is just the deflection at the middle of this simply supported beam. Okay, that's all I care about as a steel designer. I just want to know what the maximum value is. And so in this case, that's pretty simple. I could go back to mechanics and materials and just figure out where the maximum deflection is and use that in the equation. Now, thankfully, we don't have to do that all the time because somebody's already done this for us. And so you can go to the handbook on page 5-132, and it's going to give you a bunch of equations that we should already mostly know about for simply supported beams. Right? So it's going to tell us what the maximum shear force is. It's going to tell us what the maximum moment is. And here, which is what we're caring about today, the deflection, that's maximum. That's at the middle for this particular case. And the maximum deflection is going to be 5 WL to the 4th over 384 EI. Okay, so all of the joists that we're dealing with, unless the loading changes, and sometimes the loading changes, but for the simple framing we're talking about in our class, we're always going to use this equation to figure out what the maximum deflection is from live loads, from snow loads, from dead loads, whatever. Okay, so 5W84 EI, that's the magic equation to always remember when we're calculating deflections for joists. Are there any questions regarding what I've talked about so far, or why it's important that we kind of have a special place for this equation in our head before we continue on? Okay. There are other things, right? So maybe we've got a girder with a single point load. We did an example calculating moment resistance for that in lecture 20-something, I don't remember now, but the one on moment gradient and unbraced segment lengths. And so for a simple point load at the middle, again, there are tables in the handbook that tell us where the maximum moment is and what it is, where the maximum deflection is. And so for a simple point load at the center of the beam, maximum deflection is PL cubed over 48 EI. Okay, so that's an important equation to remember. If you have a girder with a single point load, pretty easy to calculate the deflection. And there's another one that's useful for us. For point loads that are spaced at equal distances apart, this is not meant to say that they're all third point, but it's just that A is the same from right hand and left hand side. There are 2 point loads spaced the same distance away from the supports at distance A. And again, we get maximum moments, which should be familiar, PX. And then we should get the maximum deflection as well, which in this case, again, because it's symmetrically loaded, is going to be at the center. And so this equation is a bit more. I wouldn't ever expect you to remember this one for any particular situation. But it depends on the distance A and the length of the beam, L. And so the maximum deflection would be PA over 24 EI times 3L squared, I think, minus 4A squared. Yeah. So if we happen to have a girder that has 2 joists loading it, then we could calculate the deflection at the middle based on the point load coming into the girder from the joists. Cool so far? This is all stuff that everyone should already know for the most part, right? Are there any serious questions or concerns about anything we've talked about so far? Okay. Well, that's all fine and good. Joists are easy. Uniform load, deflection. What do I do in this situation? There is no table in the handbook for 3-point loads. There's no table in the handbook for 4, 5, or 6, or 7, or 8, or 9, or 10-point loads. So all of a sudden, if we don't have 1-point load at the middle and we don't have 2-point loads equally spaced from the support, what do we do? Do we go back and do the moment diagram and integrate twice and then plug in L over 2? Or can we take advantage of some of the tools we already have and expand it to this case? Any takers? Anyone going to be brave and share an idea with the class? Yep.
Can you use both equations and just combine them together?
That's exactly it, right? So this is basically, we could break this up into 2 separate cases. We've got a beam with a point load at the middle. And if we can break out the loads at the outside, we've got a beam with point loads equally spaced from the support A, right? So I've got a solution for one load, I've got a solution for the other 2 loads, and I add them together. What's that called? Does anyone remember the name of why we can take the results of an elastic analysis for one set of loads, take the results for an elastic analysis for another set of loads, and add them together? What is that called? Does anyone remember? Yeah, it's called elastic superposition, right? As long as our structure remains in the elastic range, which is certainly what we want, at least under service conditions, deflections should never cause any kind of yielding in our structure, and so our beams are going to remain elastic under the types of loads pardon me, that we're doing the calculations for here. And so by elastic superposition, we can calculate the maximum deflection at the middle for the point load in the middle, and calculate the maximum deflection for the other 2 point loads, and we can simply take those results and add them together. Now, if we had a different situation, like let's just say we had maybe 4, right? 4-point loads or something like that. How would we handle that situation? Well, I would just do this 2 times, right? I would do it with A, the distance from the support to the first load. Do it again with A being the distance from the support to this load. And I've got 2 situations where I break it out. I've got 2 beams with 2 sets of loads. And so I might say that's equal to this, right, where this is A plus this, where this is equal to A. And I would add the deflections that I get from those 2 cases and add them together. Okay, so elastic superposition allows us to consider the equations that we're given in the handbook here. If we've got an even number of joists loading our girder, we can just do this a few times. And if we have an odd number, we can do the other we can do the point load and do this a few times depending on the number of joists that we have loading our beam. Okay, so this equation works that I have here as long as we have 3 point loads, right? So that's only good for 3 point loads. And if we have anything different, if they're not equally spaced, if it's not symmetric, this doesn't apply anymore, right? So it only works when we have the point loads arranged in a certain way, and in this case it's based on a symmetric loading of the beam. In any other situation, then you have to use some other kind of tool. Either you can do one with a point load at just kind of random points or whatever. Or, as we're going to talk about probably next lab, we might talk about it briefly today, you can use a structural analysis software at that point and just make your life easier and not think about it too much. Okay. Are there any questions about what we're doing here, why this process is important before we continue on? So how do we figure out what the deflections are going to be? Well, we're not using factored loads like 1.25 dead plus 1.5 live. We talked about why that is in lecture 10. We factor the loads up higher when we're doing safety checks because we want to make the probability of collapse or partial collapse or somebody becoming injured or killed very low. But when it comes to calculating deflections, what we're trying to do is prevent delamination of tiles, prevent cracking of tiles, and make floors not too bouncy. Different levels of acceptability, right, in terms of the building's use. So in this case, we use a different table. We use these load combinations. We've got dead plus live. And if it's important, snow and wind. Really, for beams, we either have interior joists and girders that carry dead and live loads, or we have roof girders that basically are going to carry dead and snow loads, right? Dead and snow loads, that one. And so we don't really have to mess around too much with the load combinations here for serviceability of joists or girders because they're either inside, dead and live, or it's on the roof, dead and snow. The thing that's important here, though, is when we're looking at portions of loads included in the dead loads, we need to be careful about how much load we're actually including in that, and I'll talk about that in a moment. The other part here is that for storage areas, like, I don't know, wherever you're storing a lot of stuff, probably library stacks would be included in this. In that case, you're going to increase the load to 0.5 live when you're doing the companion load. So in this case, you'd have 0.5 live in both of these situations. But for the most part, in your example buildings that you're working with, we are not working with storage areas, right? It's all office space. So these loads result in smaller overall effects on our beams, which is fine because we don't care if the deflection happens more often or if it's exceeded more often. Just means we have to call someone in to replace a floor tile and whatever. So coming back to this dead load, what do we do with this? Well, remember that the goal or the main objective of limiting deflections in our beams is to prevent cracking of finished floors. Okay. How much of the dead load do you think contributes to the deflection that may cause delamination of floor tiles? Not really intended to be a trick question, but it's just a question about what the order of everything being built is. You're building stuff, and in lecture 3, I showed you the example construction sequence of a structure. When the structure is done in terms of the steel contract work, you've got the steel framing there, so you've got all the weight of the steel framing. The steel deck is there, so you've got all the weight of the steel deck. And then the concrete trades come in, they pour the concrete floor, and so you've got all the weight of the concrete floor. So in terms of finished floor, the concrete's there, the plumbing, mechanical, electrical have probably already come in. They've installed their utilities for plumbing and for electrical systems, lighting, etc. And then they put the floor down, right? So the finished floor is like one of the last things that gets installed. And it depends on whether or not that's installed before or after the partitions. And so if you've got cubicles, for example, then you're going to install the partitions on top of the floor system. But if you're building in fixed partition walls, like stud walls or masonry walls, then the flooring is going to come after. So basically, you're going to have steel structure itself, concrete, all the other stuff. And so all that deflection is just sitting there, right? The deflection is what it is under the dead loads at the time that you're installing the floor. And so it doesn't really matter what that deflection is. I don't care as a steel designer, well, I do sometimes, but not in this course. I don't care how much deflection is already there. I just care how much deflection is going to come after the floor is installed, right? So sometimes we won't include any dead load at all in deflection calculations because it's already all there. But sometimes if the partitions are temporary and they can be moved, then we'll just include the partition weight and we'll include that in our deflection calculations. Okay, so I think that's what this is if I remember. So table D1 provides some deflection criteria that we'll talk about in a minute. These criteria are related to serviceability limit states, and although the criteria refer to service live snow and wind loads, the engineer should consider the inclusion of specified dead loads for some instances, and for example, non-permanent partitions, like cubicle spaces, which are classified by the MBC as dead load, should be part of the loading considered if they're likely to be applied after the completion of the finishes of floors that are susceptible to cracking. Okay, so just because we've got a table here that says 1.0 dead, that's not the same dead load that we're including in our factored load calculations for strength. Of course, they contribute to deflection of the structure overall. It's just not the deflection that we care about. Okay. So that brings us to deflection limitations. And so the building code doesn't specify deflection limitations for beams and girders. Should be 12th edition, and check that page number perhaps. But basically in the Annex D to CSAS 16, it gives us some tables that recommend some limits on deflections in our structures. For the most part, in this course, we're dealing with commercial building spaces, so these don't really apply. But industrial building spaces, especially if you've got cranes and stuff, like cranes operate, basically you've got a motor that's running wheels over the top of beams, and so you could probably imagine that the slopes and the deflections of beams, when you have something traveling along the beam, is probably pretty important. And so if you're ever designing something that's supporting cranes, really, really, really small limits on deflection, so L over 800 or L over 600. For most other floor areas, L over 300, L over 240 are pretty reasonable. This is why I asked you on assignment 0 or showed you on assignment 0 the calculation of L over delta, right? Because we were talking about a certain number, L over delta, and that's how we're basically going to be talking about the limitations on deflection. Basically, we've got delta has to be less than or equal to L over some number. And so it's pretty, oftentimes we'll just write this as L over delta has to be less than or equal to whatever that number is, or sorry, greater than or equal to whatever that number is. So in your future life, you might use these. For the most part, for your design projects, you're going to be focusing on these numbers because these are all other types of structures, usually ones that are commercial buildings. These are the important ones, so members of floors and roofs supporting construction or finishes that are susceptible to cracking, right? So tile floors, marble floors, probably even want to use a slightly higher limit or smaller limit. Basically, if you've got ceiling tiles or floor tiles that can crack, you're going to be using L over 360 as a maximum limit. If you've got carpeting or vinyl or linoleum that, it might delaminate or it might crinkle, but it's not going to crack and cause a tripping hazard as much as anything else. So for members of floors and roofs supporting construction and finishes that are not susceptible to cracking, we can use a slightly higher limit on that deflection. Okay. So far what we've talked about calculating deflection using elastic superposition, where for girders we can just take tools point load at the middle, equally spaced point loads from the supports, calculate the deflection. We're going to do that for the loads that contribute to deflection that can cause cracking. And so part of the dead load maybe, usually all of the live load and all of the snow load, depending on if we're on a floor or the roof. And we're going to compare the deflections calculated using those load combinations from the MBC to these upper limits on those deflection values. Does anyone have any questions about any of that stuff before we get into an example of how this might apply to whatever it is we're going to be looking at in the example? Okay. So let's apply this, I suppose. We're going to go ahead and calculate deflections anticipated for the W460 by 52 joist. And it says a W310 by 82 girder, but that's not right. We're going to look at the W610 by 82 girder. That's shown here. And we're going to compare them to the reasonable deflection limits from S16 NXD. Okay, so this is W610 by 82. This is a real floor plan. This is actually a floor plan in the Justice Building downtown. And so here is the joist. The joist is quite long relative to the girder. And so when we're looking at the joist, we're basically just going to be looking at uniform loads. When we're looking at the girder, we're just going to be looking at a series of point loads. And here we're going to assume that the floor is susceptible to cracking and that we have 1 kPa of dead load from non-permanent partitions. Okay, so we get to look at a couple things here. One, we get to look at the contribution to non-permanent dead loads to deflections, and we get to look at how the limits might be particularly strict for systems that are susceptible to cracking once it's installed. Are there any questions about what we're trying to accomplish here in the example before we start some of the calculations? Okay. So this is a building that we don't really know a whole lot about, right? So in our example building that we've been working with so far in the course, we know the dead and the live load and everything. Let's assume that this is office space. Why not? We're going to go ahead and calculate the deflections based on the loading. And so we've got 2.4 kPa of live load. And even though the dead load might be something like 4.8 kPa, which is what we've been working with in our example building, we'll remember here that most of this is already permanent, locked-in deflection that's there before we actually install the floors. And so the only thing we really care about is the 1 kPa of dead load that could be applied afterwards. Okay, so basically we need to go through, and this is nice to review some of the other stuff. We need to figure out what the loads on the joist are. Let's just look at this one. Doesn't really matter which one we look at. But we have to look at the tributary width, right, of this joist. The center spacing depends on the total length of the girder. The length of the girder is 6.38 meters. That's given in the question. And then we've got here EQ, 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 which on plan drawings denotes equal spacings. Okay, so we need to know the tributary width. We've got 1, 2, 3 spacings of joists. And so the tributary width for our joist here is going to be equal to the length of the girder divided by 3 spaces. That's 6.38 meters divided by 3. And so when we do that, we end up with 2.127 meters. So again, I'll remind everyone when we're doing the structural analysis, we'll keep things in meters, kPa, and kilonewtons. And so I'm not going to convert this to millimeters, and I'm going to continue to do the work with kPa. So I get kilonewtons per meter as an example for loading on the beam. So I need to know how much live load, how much dead load is present on this beam, and how much could potentially cause cracking. So basically I need to say, okay, I've got my joist that I'm working with here. Oops, come on. And I've got, maybe I'll stick with my colors for live load. Live load, I usually use green. And I have a distributed live load that I care about. We'll work with that first. So WL is equal to the live load times the tributary width for the joist. That's 2.4 kPa multiplied by 2.127 meters. And if I do that math, I end up with a distributed load of 5.104 kilonewtons per meter. So this is pretty much review stuff to this point, but good to check in and see how things are going. Does anyone have any questions about any of those steps before we continue? Okay. So in terms of deflections, right? Delta is 5 WL to the 4th over 384 EI. I suppose I should use little delta here as the symbol. And here I care about the live load, right? I want to calculate the live load deflection for this particular loading. L is for the joist. Here we've got 11.35 meters. And the distributed live load we just calculated. The only thing we really need here is IA. And in this case, everything's bending about the strong axis. And so we basically need to look up IX, right, for this W460 by 52. That comes from the handbook when we're doing these kinds of things. And so IX for this particular section is 212 times 10 to the 6 millimeters to the 4th. So when we're doing our mechanics of materials calculations, like deflection and stress, I like to do everything in millimeters, newtons, and megapascals. We'll remember that kilonewtons per meter is an equivalent unit to newton per millimeter, which is helpful. We don't need to convert it to anything. And so we can calculate the live load deflection as 5 times 5.104 newtons per millimeter times the length, which is 11,000. What was the length again? 11,350. 350 millimeters. That gets divided by 384 times E, which is 200 times 10 to the 3 megapascals times 212 10 to the 6 millimeters to the 4th. Okay. So if we do those calculations for the live load deflections, we end up with a deflection at the middle of 26 millimeters. That's about an inch. Might be a little bit difficult to get a sense for whether that's a lot. That's over 11 meters. So I think this room from right to left might be about 10 meters. So if you were to picture a beam a little bit longer than this room and you were trying to figure out if there was an inch of deflection, it'd be pretty hard to see that visually unless you're looking at it straight down like you're kind of going to shoot that as an arrow at a target or something. Pretty imperceivable for the most part, but something that's, it's there. Any questions about that calculation? Okay, so that's our live load deflections. We also care about the dead load deflections, right? So I might just draw some dead loads on top of that. And again, we don't really care what the dead loads are in total. We just care how much non-permanent dead load might be present there. Right, and so in our case here, we just care about this comes from the 1.0 kPa, which may be applied after the floors are installed. And so the distributed load for the dead would be the tributary width for the joist multiplied by the dead load. So we get 2.127 meters times 1.0 kPa. That gives us 2.1, why did I write 3? No idea. 2.127 kilonewtons per meter. Okay, so here we can do delta dead is 5 times 2.127 newtons per millimeter. Again, those units are equivalent, don't need to do any conversion, times 11,350 millimeters divided by 384 times 200 times 10 to the 3 megapascals times 212 times 10 to the 6 millimeters to the 4th. And for dead load deflection, we get 10.8 millimeters. All right, so what this tells me is, let's just picture the finished room before we have any partitions. You start to wheel in the partitions to make your cubicles for your people to work in. Once you do that, you have about 10.8 millimeters, a little less than half an inch of deflection. Then when the people come in to start to work, more or less you might get up to another inch of deflection, so about an inch and a half total of deflection acting on that particular joist under normal service conditions. Any questions about those calculations before we get to the last part of this calculation for the joist? Okay, so what do we do with these numbers? Well, we come back to our serviceability limit states tables. There's no snow on this floor, there's no wind on this floor, we don't care about that. We've got dead load a little bit, plus the live load from the people in the space, or the furniture in the space as well. And so we've got the load combination 1 times dead plus 1 times live. And so in our case here, the total displacement is 1.0 times delta dead, plus we've got 1.0 times delta live, which is 1.0 times 10.8 millimeters, plus we've got 1.0 times 26 millimeters. And that gives us a total downward deflection of 30.8 millimeters. Oh, sorry, that's not right, 36.8 millimeters. And the problem states that this is a floor that has floor finishes that are susceptible to cracking. Right? So the maximum deflection that we can have on this joist would be equal to the length of the joist divided by 360. And so delta max is equal to maybe I'll write it out here. L over 360, which is 11,350 millimeters divided by 360, and that limit is 31.5 millimeters. Okay? So we calculated the maximum deflection we expect on the joist from the non-permanent dead loads and the live loads. That's 36.8. The maximum we are allowed to have is 31.5. Is our floor joist acceptable from a serviceability perspective? No. We've got more deflection than we're allowed, right, by about 7 millimeters. And so we would need to pick a joist that is slightly deeper, something that has moment of inertia that's a little bit bigger, so that we can get that deflection down a little bit. The other thing we might consider doing, we'd say, okay, and you probably know this at this point anyway, but maybe I was being too conservative. Maybe I didn't understand how the partitions were going to work. Maybe the partitions will be a permanent fixture in the structure. Okay, so maybe they're actually permanent partitions, and I, the engineer, as a junior engineer, only listened to Dr. Steele's lecture and didn't even pay attention to why we were including dead load in it. And so someone, or the architect or a senior engineer says, no, those are permanent. If these become permanent, then they're already installed before the floor. We lose 10.8 millimeters from that total deflection, and in that case, we would have an acceptable deflection. Okay? The other thing that might work, maybe we don't actually have floor finishes susceptible to cracking. I don't know. Maybe it's any other floor that's not susceptible to cracking. Maybe it's divided by 300. And if that was the case, our limit would be 37.8 millimeters. So if our floor had finishes not susceptible to cracking, would it be acceptable even with non-permanent partitions? Yeah, right? So there are a couple of things going on here. You need to understand what the floor system is going to look like. The architect specifies that, but you need to know, is it susceptible to cracking or not? Because that can change whether or not that joist is acceptable or not. You also have to know if the partitions are going to be a permanent fixture or if they're non-permanent and it's something you can move around, because in that case, that also influences your design. Okay? Any questions about the calculation of the deflection, the calculation of the maximum limit, or any of the conclusions that we've made so far? Yep.
Would we ever use a live load reduction factor for deflection?
That's a good question. I don't know the answer to that. I would expect probably. you'd probably have a live load reduction factor because we're, again, assuming that the probability of that area getting covered in live load is probably pretty small. And that joist is long enough, right? 2.127 meters by 11 and a bit meters, that'd be more than 20 meters. So you probably have a small live load reduction factor of maybe 92% or something like that. So possibly. Good question. Anything else? Even if we had a live load reduction factor of 0.9, let's just call it 0.9, which is high for a joist, would that solve our problem in the first case? No. So if we had 90% on the 26 millimeters, then that would go down to 23.4 millimeters and something like that. And so it'd still be 23.4 plus 10.8, which would be bigger than the 31.5. But still, that's something I should consider for the example next year, is to apply the live load reduction factor for the deflection calculation. Anything else? Okay. So let's quickly look at the girder then. We'll at least set up the problem, and I'll tell you a little bit about it. We've got 10 minutes left, which should be fine. We've got a W610 by 82, and it's supporting joists on both sides at 2 locations. Right? So I am going to, I'll start here, and I might have to go back and erase some pages, but we've got a girder. It's working like this. Let's just assume for the girder calculations that we don't have, that the partitions will be permanent. It's not compatible with the joist calculations, but let's assume that we made a mistake there as the junior engineer, and that will shorten the example a little bit. So in that case, we're going to have some point loads from the live load, right? Point load, live load. And they're spaced at the center to center spacing, which is the same as the tributary width for the joist. That's, why do I keep writing 3 instead of 2? 2.127, 2.127, 2.127. Okay, so slightly different problem, different beam, different lengths, different loading. This is pretty convenient for us though, right? We've got a pretty simple loading of the beam. Why is this convenient for us for calculating deflections? Well, we already have the equation, right, for deflection of beams with 2 point loads, right? That's this one. We just care about what A is. We don't have any other loads to consider, and so we can just use this equation without having to do any kind of elastic superposition, right? So that's nice. PL, that's the total load from the live load on our joists, right? So if we come back here, basically, we want to know what the live load reaction is here for the joist, which would be the 5.104 times the 6.38. And we've got one on the left-hand side and on the right-hand side of the girder. So whatever the reaction is on the joist, we multiply that by 2. So here we get 2 times W, which is 5.104 kilonewtons per meter, times the length of the joist, which is 11.35 meters, over 2. So the 2's cancel. We just get W times the length of the joist. And the total load on our girder is somewhere here. Ends up being equal to 57.9 kilonewtons. Okay. So just statics that we should already know how to do. We've got the reaction, right? That's the reaction of on the joist from live load. We have 2 of them because we've got 2 joists framing into that girder, and that gives us a point load of 57.9. Again, probably even more likely that we could reduce this live load based on the live load reduction factor for the girder. Not something we're going to look at right now, but maybe we'll do a quick calculation at the end to see what the influence of that would be. In any case, the live load deflection for this particular girder, if we come back and look at the equation we have, this is a simple one-shot calculation of deflection. So we've got PA over 24EI times 3L squared minus 4A squared. PA over 24EI times 3L squared minus 4A squared. A in our case is equal to this 2.127 meters, right? So we've got 27 millimeters. The other thing that's important here is we need a different moment of inertia because this is a different beam. This is a deeper beam than the W410 by 52 we are looking at. And so the moment of inertia for this W610 by, 82? By 82. If you look that up in the handbook, you get 560 times 10 to the 6 millimeters to the fourth. Okay, so here we end up with P, which is the 57.9. We have to do times 10 to the 3 to get newtons. We divide that by 24 times 200, 10 to the 3 MPa. This is going to be a fun one to write here. Times 560, 10 to the 6 millimeters to the fourth. That gets multiplied by 3 times L squared, which is 6,380 millimeters, the total length of the girder, minus 4 times A, which is 2,127 millimeters squared. And if we calculate that deflection for live load, we end up with 4.77 millimeters. Okay, that's not a lot. Generally, when we frame buildings, we do tend to have the joists being a little bit longer and the girders being a little bit shorter. That just makes the ceiling a little bit shorter. And so in this case here, we have a deeper section, right? A heavier section with a higher I, and we have a shorter length compared to the joist. The loading might be slightly higher just because we have more joist framing into it. But overall, because the I value is quite high and the L value is quite low, we end up with a relatively small displacement value. What do you think, or maybe before I write anything else down, do you think that's acceptable compared to what the upper limit on that girder would be? I would think so, right? Let's just assume that the floor is susceptible to cracking, so we want L over 360. That's equal to 6,380 over 360, which would give us a limit of 17.7 millimeters. And so even if we had the strictest limit on deflection for our girder, we're well within that limit, right? We're not including the permanent dead loads there. If we had non-permanent dead loads, we could include a little bit more deflection from the non-permanent dead loads, but we'd still be at a deflection that's well within the upper limit on deflection for the girders. Deflection tends to be more important for joists than for girders for this reason. Girders tend to be deep, they tend to be short, whereas joists tend to be not as deep and they tend to be longer, meaning deflection is more likely to govern the design of those members. Okay, so just to recap very briefly, we have a joist and we have a girder. We just want to know what the deflections are on those elements from the loading present, and we want to compare them to the acceptable upper limits. We got some distributed live loads, some distributed dead loads, and calculated the dead and live load deflections. We factored them together to get a value that exceeded the limits, but we talked about some ways that the limit may be met based on the design of the joist, whether the partitions would be permanent and whether the floors would actually be susceptible to cracking or not. Assuming that we were a little too conservative and we actually have permanent partitions, we just looked at the live load deflections on our girder. Don't need elastic superposition here because that's a straight shot equation. Get a value that's much lower than the limit, and so the serviceability limit states for the girder are most certainly met, and that's even before we apply a live load reduction factor on those values. Does anyone have any questions about that example before we move to wrap up the lecture for the morning? Okay. Well, I don't know why I always do that. We're missing a few there. Should be able to identify the loads that contribute to deflections with potential to damage floor finishes. That's basically whatever is going to be on the floor after cracking, and sometimes that can include some non-permanent dead loads. We've got to be able to calculate the maximum deflection for simple beams using the MBC load combinations and compare those to maximum deflections from S16 and XD, and we did that in the example at the end for both a joist and a girder. Are there any questions about anything that we talked about at all this morning before we call it a day? Cool. See everyone this afternoon then in lab.